Chapter 17. We say the roughest chapter for the next to the last one. We'll fry your brains on this material, and then we'll relax chapter 18, because that's all electrochemistry, batteries and stuff. But this one is really difficult to wrap your brain around. I'll give you a fair warning. And I'm not so sure that there are that many chemists that understand it. But some of the basic concepts can help us hopefully understand why reactions occur. In other words, when we say spontaneous, we mean they occur with no help. I mean, that's the natural direction they want to go. All right, so let's get a little background information first. We studied, first we studied kinetics, right, reaction rates. Okay, then we used what we knew there to understand not thermodynamics, but equilibrium. And equilibrium is sort of a subcategory of thermodynamics. When we look at a reaction, remember this general reaction progress and energy diagram for a reaction. We have reactants here and products here at these different energy levels. And then you have to add enough energy to get them over that hump. Activation energy. Recall that a little bit. Yeah. Okay. These zones in here, this part in here is where we studied kinetics, or the reaction rates. So what we learn about this tells us about reaction rates. What we learn about this, just where we start and where we end, doesn't matter how we get there. That is a study of equilibrium, and now we're going to expand that into thermodynamics. And thermodynamics is just, well, look at the word. Thermo means heat. Dynamics means movement. So heat's going to move. But it's not just about heat. It's just that was a convenient term, and it might have been grandfathered in. But it covers the territory of reactants and products, and we only need to know where we start and where we end. How we get there is irrelevant. So that's, and that's just the way things are organized. In other words, like I've always said before, nature just does what it does. It goes from here to here, and it goes there at a certain speed. And it's our job to figure it out. Okay? So, kinetics is a path function. In other words, it does matter how you get there. For instance, when we use a catalyst, that gives you a different mechanism to get to products. In fact, a mechanism that gets there faster. So this is the path, a study of path functions, whereas thermodynamics is study of state functions. Okay. So with an understanding of thermodynamics, we can predict the direction of any process. In fact, it doesn't have to be a chemical process. It could be physical too. But we don't have any information about the speed of the reaction, only the direction. And the best illustration I can think of, thermodynamically speaking, diamond is unstable. That is, it will spontaneously degrade over time. But it'll take it maybe 2, 3, 4, 5 million years to get there. Right? So the kinetics of diamond degradation is one thing, thermodynamics is another. We can say what direction it's going, we just can't say how fast it's going to get there. But we want to understand spontaneous processes, ones that occur without any intervention. And I hope by the end of the next 3 or 4 slides, you'll understand why we want to do that. Consider this problem. You have a gas confined, 2.4 moles of gas confined in a container with a valve, and it's connected. This one is 4 liters, I think. Yeah, 4 liters. And this one is 20 liters. This one is a vacuum. So you have 2.4 moles of gas in here. Okay? Intuitively speaking, you know what's going to happen when we open that valve. It's going to go whoosh, and then equilibrate. Right? We've already studied gases in those terms before and after. So using Boyle's law, if we open this up, we can figure out, if we know the pressure over here, we can find the pressure over there. Because it's constant temperature at 32 degrees C. So we know what's going to happen. We just need to digress for a moment and review some terms, refresh our memories. Delta H is enthalpy. That's a kind of second cousin to heat movement. But enthalpy is more like a potential for heat movement into it or out of a process. And it's also can be equated. I think we introduced this without describing what it was. Delta E plus P delta V. We used this equation in a previous chapter to describe when we could equate delta H with Q. And that's when pressure is constant. But this equation is one that we'll be looking at again. Internal energy. We know that internal energy can, well, this is one expression for internal energy. Change in internal energy can be associated with any changes in kinetic energy plus any changes in kinetic potential energy. But remember, we also said it was Q. Let's see. That looks too much like a G. It's Q plus W. Right? Any heat movement plus any work done is delta E. So we can look at it 2 different ways. And I just defined these 2. Actual heat movement or actual work done. Okay, so now we got those refreshed. Let's look at this same problem again. Now, what if we calculate delta H, delta E, Q, and W for that? We did that for a previous chapter. And we determined that all of these values are 0 for this type of process. And here's the re-explanation. If the process is at constant temperature, then you're not going to get any heat flow at all. Delta H and delta E have to be 0. And since the gas is working against 0 pressure, I mean, there's no resistance at all. So no work can be done. Right? You need to be able to apply force through a distance, and you can't apply force when there's no resistance to it. So work is 0. Let's see. I didn't put Q in there. Q is 0 also.
Yeah, it's at the bottom.
Oh, we're saying, okay, we're deriving Q is 0 here. If delta E is 0 and W is 0, then Q has to be 0. All right, so all those factors are 0. So why do we go to all this trouble? Well, this happens. We just have to explain it. We can't explain it with these terms because none of them are changing. Right? So what's the driving force? Well, we have to create a new term. as luck would have it, that term is S, stands for entropy. And it was proposed by this fellow right here, Rudolf Clausius, about the time of the Civil War. Of course, he wasn't in this country at the time. I think he's maybe German. You remember Clausius from chapter 10, our very first chapter, where we were able to calculate the enthalpy of vaporization if we know two processes. Right? The vapor pressure at this temperature and the vapor pressure at that temperature, we can calculate the delta H of vaporization. That's the Clausius-Clapeyron equation. Right? And I didn't have any memorize it because I put it in useful information. That's just a stroll down memory lane. Okay, so here's a representation of what we might see here. In this case, it looks like the volumes are equal, which is fine. So you've got all this ideal gas in here and a vacuum over there. When you open the valve, it's going to spread out and it's going to equilibrate. Right? You're going to have the same number of molecules on both sides. Right? The molecular density is going to be uniform throughout. Okay. The difference between the images is that the second image allows for the same number of molecules, but in a larger space. They got more room. So that's key to what drove this process, is the fact now that they have more possible positions. The community's expanded, but there's the same number of people. So they got more elbow room. And that is an expression of increased entropy. Notice we're using gases again. So some of the best understandings of chemistry and physics come from gases. So there's no coincidence. It's just easier to understand problems when you work with gases. And then once you understand gases, then you sort of you morph your understandings into liquid and solid phase systems. Okay. So if this driving force we call entropy causes a spontaneous process, then the entropy, as we describe it, has to increase. The S number has to get bigger in a spontaneous process. So that's what we're saying here. Any change in entropy greater than zero is, well, sometimes we refer to it as disorder, right? An increase in disorder. Now this is it can also be viewed as randomness. And we always calculate S as a change, a delta S. And the reason for that is we can't get to an absolute position with S. So if you see S, it's, I would say 99.999% of the time, it's a delta, even if the delta is not there. Okay, when we speak of entropy as a disorder, that's a useful analogy, I should say. But it's not technically correct. Oh, somebody's been smearing stuff on my board again.
Oh, that's awful.
That's terrible. They're probably using this stuff. That's what we use it too. Polish. I used to think that was good stuff, but I found a better combination. This COVID thing, I had to work off the whiteboard all the time from my home. I was using whiteboards that were just, they were wore out. So I figured out, I did some research, and I figured, clean it just as crystal clean as you can get it. And I found the most effective way to get all that stuff out was Goo Gone. You know, that orange stuff. It has a citrus smell to it. Use Goo Gone, and you can get that all off of there. And then clean the Goo Gone off with isopropyl alcohol. You get it just perfectly clean. Then get another clean rag, and these microfiber rags, they work really well. And spray some WD-40 on it. And rub that on, just a very, very thin coat. And I always put too much at the beginning, then I flip it over and then I rub all that off. What it does, it gets down in the pores and seals them off. So this stuff will get down in the pores and get hung up. And it seems to work pretty good for a while anyway. Okay, back to our topic. So it's useful to think of entropy as a measure of disorder. And that works in many cases. So entropy in reality describes the number of arrangements that are available to a system. That is, and it's probably best described in a picture, probably on the next slide. We're talking about probabilities again. Right? When we discussed at the end of Chem 101 the bonding theories, we eventually settled on a probability-based theory. So we're still here with probabilities, and the natural state of any system is toward the one that allows for the highest probability of existing. And that means you have more possibilities for arrangements. So when you increase the volume of that gas, it gives it more places to go. So you have more states that it can exist in. We call those microstates. So here's an example. If we have this bulb, these two bulbs connected, and say we start off with 4 molecules, A, B, C, and D. Okay, that's one microstate. If they move, all of them move over to this side, that's a different microstate. Okay, so this is one here, and this is the other one there.
So, just using this as an example, those little weather things, you know what I'm talking about? It's a tube and it's filled with liquid and it's got bubbles in it and it's supposed to tell you the weather or whatever.
Are you talking about what's the name of that?
I can't.
It measures the temperature, right? Or does it measure the pressure?
I think it's the pressure. So that's how it does.
Because there's one for temperature too.
It like measures the pressure of what's going on.
Mm-hmm. Well, whatever works for you. So there's only one possibility for this arrangement, right? So it has very low probability of existing. The higher the probability, the more different arrangements of the same numbers. So if we put 1 on either side and leave 3 behind, we can have 4 possible states. Right? If we leave all 3 on this side, all 3 on this side, all 3, just move 1 to the left, then you have 4 possible states. If instead you go up here and you take 1 from that side, put them over here, those are different states. These are a different set of microstates, but they're 3 1s, 3 1s. Instead of 4 zeros, there are 3 1s, 3 1s. There are 4 of those. This one is 1 3s. So those are a different set of microstates. You don't combine these two. These are separate. But if we allow for 2 in each side, we can get combinations that will give us 6 different possibilities for those particular arrangements. This is the most probable arrangement, where half is on one side and half is on the other. Right? So that's the most probable arrangement of microstates for this example. And you could do that with more, but it would take, you'd have to do it inside a computer. There's not enough board space to do it when you start adding more molecules. Okay. So this is in words. Each of these configurations gives you a unique arrangement of particles. This configuration, 2 by 2s, give you 6 arrangements. These 1 by 3s only give you 4, and these 0s by 4 only gives you 1. Okay, so let's look at it in a practical sense. If we say we're going through a phase change, and we start off with a solid, and we move to a liquid, and then we move to a gas. So the number of microstates available to the solid is very, very limited because they're locked in a crystal structure. Right? So they're very, very low entropy. But if you turn it into a liquid, now they can move past one another, and they have more possible microstates. But if you expand it into a gas, you actually take this number of molecules and expand them into a gas. And the rule of thumb is when you go from liquid to gas, you increase the volume by about 1,000, factor of 1,000. So you give it a lot more volume. So more microstates are available. So the entropy progression is from low to middle to high entropy. Gas has much more entropy, more microstates possible than liquid does, which has more than the solid. So we would expect, based on entropy, since the natural systems tend toward higher entropy, we would say that from a thermodynamic standpoint, the natural spontaneous movement of the system is from solid to liquid to gas. Okay. What I'm going to talk about now is not in your textbook. And the reason I bring it up is because my hope is that this part of the discussion will help clarify some things. So we're back to system and surroundings concept. Like we started off with thermochemistry. Okay, and we can confine the surroundings like this. Right, we don't have to use the whole universe. So when we consider the total randomness as a combination of these two, we add their randomness together, their entropies together. And exothermic process implies an increase in energy randomness for the surroundings because we're moving energy from inside the system to the surroundings. So the surroundings increase their entropy based on the energy input. And the way to think of that is all these molecules out here, now they're moving faster. They can get where they're going quicker. You can shuffle them around quicker. You have more potential microstates because they're moving with much more energy. But that's only a conceptual description. Right? What actually is happening is The microstate concept itself is energy driven. In other words, if you have more energy in this packet, that by definition is higher entropy. So when we talk about exothermic processes, the surroundings are increasing in entropy, but the system is decreasing in entropy. But the total entropy is constant, right? So there's no change. There's no change in entropy for this whole system surroundings. But inside here, the entropy here, change in entropy is greater than zero, and the change in entropy here is less than zero. But the total of the two is zero. Okay? Because this is an isolating barrier. Nothing gets in, nothing gets out. Matter doesn't come in or go out, and energy doesn't enter or leave. Okay? That's the only way that we can say this right here, is if it's isolated. Okay, so an endothermic process is a decrease in energy randomness for the surroundings. And we're going to differentiate for the sake of discussion, energy randomness is one way of describing it. And what's the other term? Maybe it's on the next slide. I want to say physical randomness. I hope I used the right term. So you can think of entropy in these two terms: energy randomness or physical randomness. Our first discussion. Yeah, go ahead.
On this one slide, it says positional randomness.
Positional, thank you. Energy versus positional. So we started our discussion with positional randomness. And now we're going to introduce energy randomness. Okay. So let's see if we can determine, qualitatively speaking, the sign on the delta S for each of the following. So increasing randomness of either kind is a delta S is positive. So we're looking for delta S with a positive sign or negative sign, but that's our basis. The evaporation of alcohol. Okay, alcohol is going from a liquid to a gas. So its randomness is increasing, right? It should be positive. I'll come back to that in a second. There we go. Freezing of water. So it's going from a liquid to a solid, should be negative. Yeah. Compressing an ideal gas at constant temperature. You're decreasing the randomness, right? As opposed to allowing the gas to expand into a vacuum, we're pushing it back into that other bulb.
So this is negative?
Yeah, it should be negative. And we can't say anything about the energy because it's at constant temperature. Heating an ideal gas at constant pressure. Now you're increasing the energy randomness. So that would be positive. And dissolving sodium chloride in water. So you're given the sodium and the chloride ions more places to go. Yeah, should be positive. Now let's see, why did I put that one up there? Delta S cannot be measured directly. That's true. It has to be calculated using the Boltzmann equation. And actually, that's a simplified version of the Boltzmann equation. I think there's one that's probably more useful than that, and we're not going to do it. It's probability. It's mathematics driven. Right? It's not practical measurement, science driven. But it was necessary to explain spontaneity because no other explanation worked. I used to think, in fact, when I first was introduced to this topic, I convinced myself on the spot that entropy was a figment of somebody's imagination. It wasn't real. But now, after I've had a chance to work with it a little bit, it was a necessary development to explain a natural phenomenon. Okay. Okay, remember the first law of thermodynamics. The first law of thermodynamics. Change in energy of the universe is equal to 0. It's conservation of energy throughout the universe. Okay, the second law introduces entropy. Okay. In any spontaneous process, there's always an increase in the entropy of the universe. So the entropy is becoming more disordered, is one way of thinking of it. It's increasing its microstates. Now that's for the whole universe, the entropy of the entire universe. When we discuss localized problems, we can isolate a system and surrounding, and that becomes our universe. And in that case, the entropy, well, if it's isolated, the entropy has to be 0. So that's why I said you can restrict the definition of the universe by isolating the system and surroundings. I think the authors of the textbook, they tend to conflate the whole universe with this isolated universe, and that's dangerous. So I try to differentiate between those two, especially in review problems. So the entropy of the universe is increasing, yep. The total energy of the universe is constant. That's the first law. But the entropy is increasing. So we can say that the change of entropy in the universe, whatever that may be, is equal to the change in entropy in the system plus the change in the surroundings. And in this case, I prefer to use universe as our isolated universe. It's easier to study that way. Okay, so I've chosen, what I tried to do in review problems anyway is whenever I pulled out a review problem from a test bank, and it said universe, and I read through the problem and their solution for it, and I said, they're not talking about the whole universe, they're talking about total, right, for our isolated system surroundings. So in that case, I try to change all of those universes to total. So the total change in entropy is equal to system plus surroundings. Okay. So if we can measure the change in entropy for our isolated system surroundings, you know what? That's not always true. Delta S equals 0. Because if there is energy stored, well, let me not flog that horse right now. Let's just get through this first. I think hopefully it'll work itself out. What we want to find out is the delta S total. If it's positive, then we're saying that the entropy is increasing. it's negative, then the process is spontaneous in the opposite direction. So when we determine those signs for the individual processes, the ones that were negative were not spontaneous in that direction. They're spontaneous in the other direction. So it's like any equation where you say A yields B and delta H is, say, negative for that process. Then if we reverse it, then the delta H would be positive. Okay, it just goes the other direction. I think that polish helped. Okay, if the delta S total is equal to 0, then the process has no tendency to occur. We're at equilibrium. So this is an important relationship to remember. If delta S, if the total delta S is equal to 0, then we're at equilibrium. Okay, now we're going to look at, this is probably where you saw positional randomness. This process, we're going from liquid to solid. Which direction involves an increase in energy randomness? Increase in energy randomness. So the molecules are moving faster if we go from right to left. So that implies energy randomness from the reverse direction. Positional randomness also. So let me see, am I right? This would be exothermic this way. As it goes from liquid to solid, it has to give up energy. Energy randomness favors the formation of the solid. Okay, so releasing energy increases randomness, energy randomness. That's what they're saying. I would have thought the other direction. See, that's what's a problem with this whole universe that Clausius opened up. All right, let's leave that for now, and we'll hopefully come back to it. Exothermic process from liquid to solid, that should be spontaneous going from liquid to solid, but the other direction, positional randomness, should go the other direction. You're going from solid to liquid. So I see what they're saying. When you're expelling energy into this environment, you're increasing the energy randomness for the whole system surroundings. Whereas the positional randomness goes the other direction. So I'm thinking that there's a balance here. So which one is bigger? If the value for this one is bigger than that one, then the reverse is going to be spontaneous. But if the positional randomness is greater in magnitude than the energy randomness, then you're going to see movement to the left as spontaneous. So we have to look for the balance between the two. Okay, so under different circumstances, temperature increases for one circumstance, temperature decreases for another. Which one takes precedence? Let's see, as temperature increases, positional randomness dominates. As temperature increases. I don't see that yet.
That's so confusing.
Yeah, I don't see that yet. As temperature, are we still looking at that same process? If we're going from a liquid to a solid. Positional randomness favors this direction. And energy randomness favors that direction. Okay. So if temperature increases, No, that doesn't make a bit of sense. I would have thought the other direction. So this is a qualifier. At high temperature, positional randomness dominates as the release of energy becomes less important. Oh, okay. So look at it this way. When you are at low temperature, a change in temperature is more significant. Right? If you go from 10K to 20K, that's a huge difference. I mean, it's a doubling of temperature. But if you're at high temperature, a change of temperature is less significant. So my example was, we go from 10K to 20K is a doubling. But at high temperature, say 800K, if we go the same 10-degree movement, 810K, that's a very, just a minor tick, right? So at high temperature, this same change in temperature is less significant. So that opens the door for positional randomness to dominate. Okay, does that make any sense?
I think so.
Okay, at least this time around. Okay. Okay, so as the temperature decreases, energy randomness is favored and positional randomness becomes less important. Positional randomness becomes less important because we're moving toward a solid, like from a gas to a liquid to a solid, and the molecules are more restricted. So the availability of microstates becomes almost non-existent. Okay. So at what temperature is there a balance between energy randomness and positional randomness? At equilibrium. When you're at equilibrium, then they're in balance. And that's melting points, boiling points, right at phase changes is when those two are in balance. I'm gonna leave that up there for a second. I'm gonna leave it again. Okay, how about other changes? Describe the following as spontaneous, non-spontaneous, or can't tell. So an exothermic, a reaction that is exothermic and becomes more positionally random. More positionally random. If it's exothermic, we said that exothermic favored energy randomness and spontaneous and yeah, they're both positive, aren't they? Mm-hmm. Yeah, so that one should be spontaneous. Yep, right. Exothermic, that becomes less positionally random. Can't tell. We got to know the magnitudes because one of them favors and one of them doesn't favor. Yeah. How about this one? Endothermic and becomes more positionally random. That's another can't tell because they're opposing. And then endothermic and less positionally random, that's non-spontaneous. Both of those processes are unfavorable for spontaneity. Okay, so I think the whole point of this discussion was to try to get a handle on the concepts of energy versus positional randomness and when each is operable or most favored. So it says A and D are not affected by temperature. A and D are not affected by temperature. Endothermic takes in energy and becomes less positionally random. Oh, okay. They're not affected by temperature because they're both spontaneous driving forces for this one and non-spontaneous driving forces for that. So temperature doesn't matter. Right. These are temperature dependent. So when you have an exothermic process that's less positionally random, then you have to consider which one at what temperature. So I would think if it's less positionally random, a high temperature would favor this one. And this one would be favored by a low temperature. Let me see. Maybe they're going to tell us and maybe they're not. So if we just focus on the entropy of the surroundings in our isolated system surroundings setup. The sign on the surroundings, entropy, depends on the direction of the heat flow. Right? Well, that makes sense. Right? What direction is the heat moving? Right? If the heat moves out of the system, then the surroundings are going to become more energy random. So exothermic processes favor randomness in the surroundings. Okay, I'll buy that. But as heat enters the system, randomness in the surroundings has to decrease. Now this is randomness I would assume that since we're focusing on heat movement, that this is energy randomness predominant. And the magnitude of this change depends on the temperature. So if it's at high temperature, this change is very low. It's very little change. But if we're at low temperature, the change is much, much bigger. Right, if we start at a lower entropy, then the at lower temperature, the change in entropy has a greater effect. So we're saying delta, the entropy change for the surroundings is directly proportional to the heat transferred and inversely proportional to the temperature. Okay. We're saying delta S for the surroundings is as proportionality. Is directly proportional to the heat and inversely proportional to the temperature. Okay. Okay. So they're actually saying they're equal. No proportionality constant required. So delta S of the surroundings is equal to the heat transfer divided by the temperature. In fact, they're not even saying delta T, they're just saying T. So the units of measure here for this say that it's going to be joules per K. Joules per K. So if this is true, and we want this to be spontaneous, then this has to be positive, and then we have to look at these two. For an exothermic process, this is negative, exothermic process. Oh, for the surroundings, now we're looking at these processes in terms of the surroundings. Up to this point, we've said everything is referenced to the system. Now, the system will experience a loss of heat because it's exothermic, but the surroundings will have a positive gain of heat. Okay, so that's why this value is positive. And endothermic process is negative for delta S for the surroundings. So if this is at constant pressure, now we can say that's delta H, enthalpy. This is at constant pressure, just like before. That's the only time that these two could be equal. Oh, and this is negative. Now, you understand why that negative is there. Because delta H is in terms of the system. Right? So if we're going to say something about the surroundings, we have to change the sign. Okay. Just checking. And T is always positive because it's Kelvin. Okay. All right, we've talked about this before. Enthalpy and Q are completely different values. Enthalpy is potential, similar to internal energy. So here we have our, like we did before, when we were talking about thermochemistry. Oh, I'm going through the same process as before. This justifies delta H equal Q if P is constant. Okay, so you're getting it again in this chapter. Okay. Now, I'm gonna leave that up there. So if the, now, since I pulled this table out of the textbook, they're going to be using delta S universe when they mean delta S total. If the delta S for the system and the delta S for the surroundings are both positive, then the delta S for both of them together, the sum is positive. That means this process will be spontaneous. If they're both negative, no reaction will occur. The process is not spontaneous. And then if they have different signs, it all depends on the magnitude. Which one's bigger? Okay. So we can work problems using that concept, but it's not as useful. I mean, it's sort of useful in understanding how processes work, but there's a better way. This fellow right here, Josiah Willard Gibbs, was a brilliant chemist. And he was approaching thermodynamics with his knowledge base. And he was interested in how much energy can be extracted from a process. And he called it free energy. How much is available to actually do work? Because he knew, based on the other concepts of entropy that had been introduced before, well, simultaneous to his work. He was probably a colleague of Clausius. He understood that to be useful, these concepts needed to express something about how much energy we can gather from the process to do useful work. So that was, and he's not the only one that was working with free energy. There are other concepts, but his is the most commonly used. And this is not a training ground for future chemists. So we're going to just focus on one. Okay. So he came up with this equation. The free energy, the change that gives you this free energy, is equal to whatever the enthalpy of the reaction is, minus this factor, which is the lost energy to entropy. So he knew that you had to subtract out the entropy from the enthalpy to find out what was left over to do useful work. Okay. So that delta G equals delta H minus T delta S is known the world over as Gibbs free energy formula. If we divide everything through by T, that's all we've done here. Well, actually negative T. Divide everything through by negative T, then that puts delta S out here by itself. Okay, so I think you know where I'm going with this. We're going to solve for delta S, I'm pretty sure. If we know that delta S for the surroundings is this value, then that's why we divided everything through. Let's do it like this. I think you can follow along, and I'll be able to follow it myself if I do it like this. Minus T delta S. So we're going to divide everything through by minus T. Okay, we can do that. That's mathematically allowed. So now we get this one, that one, and this one cancels the T's and make this one positive. So this now is a positive delta S. Okay, that's where we're at right here. But we also know that delta S for the surroundings, and this is total. Right? That's the total delta S. Delta S for the surroundings is equal to negative delta H over T. And notice that this one is the same as that. So now we can say this is equal to delta S surroundings plus delta S total is equal to negative delta G over T. So that's where we're at right here. Wait a minute. Hold on a second. Excuse me. I misspoke. If we don't have a subscript, assume it's for the system. Yeah. It should be like that. There we go. So now, delta S for the surroundings, delta S for the system equals delta S total. So that means delta S total is equal to negative G divided by T. So now we can get a handle on the delta S for the total is equal to Gibbs free energy divided by T, take the negative sign. And that's a useful equation also. And this is at constant temperature and constant pressure because it was derived from delta H, which had to be at constant pressure. Okay. So what we're saying is this process is spontaneous in the direction in which the free energy gets smaller. So if this one gets bigger, this one has to get smaller, has to be more negative in order to be positive. So the smaller delta G gets, the bigger this side gets. So all we're saying is negative delta G is says a spontaneous reaction. If the sign on delta G is negative that says, I should use this, says spontaneous. So now we've got two ways to look at it. If delta S total is positive, we've got spontaneous reaction or process. Negative delta G is also spontaneous. Okay. Let's say a liquid is vaporized at its boiling point, constant pressure. Predict the signs here. So let's see, if it's vaporized at its boiling point, we're saying that it's at equilibrium. So as it vaporizes, we assume that it's working against a pressure. So now that it's working against a pressure, not going into a vacuum, but it's being opposed, it's working into a pressure, then the system is losing work. The system is doing work on its surroundings. I'm sorry?
So it's gaining heat, right?
It is gaining heat, yes. But okay, we're going to the next one.
Sorry.
Yeah. Gas does work on the surroundings, yeah. So it's gaining heat, right? Heat is required. And if it's at constant pressure, then delta H also has to be positive. How about delta S for the system? Well, if the system is the liquid, then the liquid is becoming more and more random. So it should be positive. Yeah. More disordered than the liquid. How about delta S for the surroundings? We're adding energy to the surroundings.
It's negative.
No, we're extracting energy from the surroundings. So that should be negative. Yes, you're right. So the surroundings are supplying the heat for this process. And how about delta G? Well, let's see. Delta G is related to delta S total. So plus and minus.
So is it just zero? Is it just even?
Yeah. That's right. That's right. Because we're at the boiling point, we're at equilibrium. Thermodynamic, entropy speaking. Right. So these have to be equal in magnitude, opposite in sign, which means delta G has to be equal to zero. Because it's total. Yeah, that's true. System is it. So whenever delta G is at zero, just like delta S is at zero for boiling point or freezing point, then these values are zero.
I just look at it when it's the system and the surroundings. I just look at it as one. Each of them is one. So if it doesn't have anything with it, and it's a system and it's +1, and then the surroundings is -1, it's zero. That's just how I look at it.
Okay.
Because it just helps me I just think it's just one. Because 1 subtract 1 is 0.
Okay.
That's how I'm looking at it.
Yeah, that's a good way to think of it. I mean, conceptually speaking, it works. Yeah. Okay, so under those circumstances, if we say that delta H equals T delta S, so let's go back to our Gibbs free energy is equal to delta H minus T delta S. So what we're saying is, if this is zero, then this has to be equal to that. Because this gives it an opposite sign, and they cancel each other out and become zero. So if we say this is zero, then you solve for each one, then delta H equals T delta S. Okay, so let's see if we can do some calculations here. we've been working on concepts, and concepts are okay, but real chemistry, real physics happens with problem solving. So if we, let's see, the value of delta H, the vaporization of a substance, is 45.7 kilojoules per mole. And its normal boiling point is 72.5 degrees C. Normal boiling point is 1 atmosphere pressure. And yeah, 1 atmosphere pressure. We can't say normal temperature because temperature is different. Okay, calculate delta S system, delta S surroundings, delta G for the vaporization of 1 mole of the substance. Well, if it's at its boiling point, delta G will know is 0. Know that delta G is 0. How about the others? Well, they would have to be equal but opposite in sign, because if delta G is 0, then delta S total is 0. So if we say that, let's see, we know what delta H is, 45.7 kilojoules. So surroundings is minus delta H over T. So here's our delta H minus sign, then divided by temperature in Kelvin. And this is our delta H, delta S for the surrounding. Okay. And that means that the delta S for the system is positive 32. Okay. That's pretty simple.
Professor Dave here. Let's learn the laws of thermodynamics.
He knows a lot about the science stuff. Professor Dave explains.
The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept, entropy. Entropy is quite difficult to understand, but we can most easily describe entropy as disorder. And the second law states that the sum of the entropies of a system and its surroundings must always increase. In other words, the entropy or the disorder of the universe is always increasing. Within a system, there is also a tendency to go towards higher entropy. The classic analogy is that your bedroom will over time become messy, but it won't suddenly become neat. Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy. Yet another way is to analogize entropic states to computer code. Let's take, for example, an ionic solid compared to the same substance as a liquid. Clearly, the solid state is more ordered and the liquid state is more disordered or higher in entropy. To describe the solid state using computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and many other things. But to describe the liquid state, you would need to simply describe the volume of liquid and the shape of the vessel, because the motion and configuration of the molecules are random. That's far less information that needs encoding, which is a way of rationalizing why increasing the entropy of a system is thermodynamically favorable. We can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot coffee cup into the table or your hand because the heat energy will be more disordered if more dispersed. This is why heat spontaneously flows from hot to cold and not the other way around. entropy. The third law states that a perfectly crystalline solid at absolute zero has an entropy of zero, as this is the most ordered state the substance can be in. Entropy is measured in joules per Kelvin. Note that entropy is not a measure of energy itself, but of how energy is distributed within a system. It is enthalpy, the thermodynamic quantity we learned about before, that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system. G, or Gibbs free energy, tells us whether a process will be spontaneous or not, meaning if it will simply happen on its own. Change in Gibbs free energy is given by this equation, which includes change in enthalpy, change in entropy, and temperature. If delta G is negative, the process is spontaneous. If positive, it is non-spontaneous. So we can use this equation to see how a spontaneous process can be either enthalpically or entropically favorable, or both, but not neither. For example, if delta H is negative, which means exothermic and energetically favorable, and delta S is positive, which means an increase in entropy, which is also favorable, a negative minus a positive will always be negative, or spontaneous. If the opposite is true, and both are unfavorable, we have a positive minus a negative, which will always be positive, or non-spontaneous. If only one of the two is favorable, we have to do some math. If delta H is positive or endothermic, that energetic unfavorability could be outweighed by the other term if the process is entropically favorable. And since T is here, this factor will increase with a larger T, so entropically favorable processes are more likely to be spontaneous at higher temperatures. Conversely, if it is energetically favorable but entropically unfavorable, the entropic unfavorability will be minimized at lower temperatures. This is a very important equation to understand, because it describes all of the spontaneous processes in the universe. There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously. But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable. An example of this is soap. You need soap to wash non-polar dirt and grime off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long non-polar tails, which allows them to spontaneously form structures called micelles. These are spheres where the soap molecules orient themselves with the polar heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the nonpolar tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water-soluble due to the polar heads facing out. That's how soap works. And that's also how highly ordered structures can form spontaneously if by enthalpically favorable or energy-storing processes. In this way, systems can defy entropy on the small scale. But the second law does hold true in that the entropy of the universe is always increasing. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
So here's what you can expect if we use Gibbs free energy equation. All we have to do is say, all right, what is the sign on delta G based upon the magnitude and the sign on these factors? So if we have delta S for the system is positive and delta H is negative. So delta H would be negative, that's a good sign for spontaneous. Delta S is positive, so the term is going to be negative. That means that both of them together will be negative. So it doesn't matter what the temperature is. Under this situation, the process is spontaneous. Let's go down here to the other end. If delta S is negative, that means this term is positive. And delta H is positive, that term is positive. Delta G is positive. So this process in the forward direction is non-spontaneous. But that also tells us in the reverse direction, it is spontaneous. And then these other two, where you have delta S positive and delta H positive, is our first example. Under what circumstances would this be spontaneous? Right? If delta H is positive, that's a negative value. It's exothermic. It's endothermic. Endothermic process that is increasing entropy. So if the entropy is highly favored, then it's a negative term that's bigger than delta H. That means it's spontaneous. So under the circumstances here, the best circumstances for this one to be spontaneous, where both are positive, is where delta S is very large, or T is very large, very high temperature would favor this one. And just the opposite here. If delta S is negative, we would want either a low delta S or a very low temperature, or both, when delta H is negative, so that the overall will be negative. Okay? Sometimes it's easier if we're trying to think through this to draw a picture. Just say you got delta S here, delta H here, and delta G here. Right? And then write your expression here. Right? So if this one is positive and this one's negative, then this is always negative. If this one's negative and this one's positive, this is always positive. Okay, that's the way I look at it. Instead of putting it in words like this, I think this is easier to comprehend. And then when you get both of them positive, then you want this one to be high temperature and or high entropy would make it spontaneous. If it's negative, then you want low temperature. You want to diminish the size of this, so this negative will come through. Okay, that's the way I look at it. Okay. Let's see. Gas A2, so diatomic gas, reacts with gas B2 to form gas AB at constant temperature and pressure. The bond energy of AB is much greater than that of either reactant. Let's look at that. Put A2 plus B2 yields AB. So we have to have two of them. And then constant temperature and pressure, TP constant. Okay. The bond energy of AB is much greater than that of either reactant. So we're storing energy. We're breaking these bonds for these two. And then we're storing some energy in here. So if the bond energy here is greater than here, we had to add some energy from this side. Right? It couldn't have come from here. It had to come from outside. I think. Bond energy of AB is much greater. Well, not necessarily. Okay, so the total energy here of this situation is greater than the total energy here. So if the total energy here is greater, that means it had to be endothermic. Yeah, so I was right the first time. You do have to put energy into it. So this is an endothermic process. Predict the signs of delta H. Okay. Oh, I just threw this one out here. So delta H, if the energy released is less than the energy required, then we're going to have a positive delta H, which makes it endothermic. Yeah. Wait a minute. Hold on a second. The bond energy of AB is greater than that of either reactant. If we react AB to form AB, that's why I put this formula up here, because you could make the mistake that I did. The energy of the bonds broken, we have to break these bonds. Oh. I was right the first time. Energy is going into the system. So it makes it, no, that's endothermic. The way I wrote it. The energy of these bonds is greater than the energy of these bonds. Okay, your instructor is confused. Okay, how much energy does it take to break these bonds? So much. But how much energy do we get back when the bonds form? Okay. If these are stronger bonds, they're going to release energy. Right. Okay. This is exothermic. So we are going to have energy over here. What we're saying is that the amount of energy that has to go in to break these bonds is less than the amount of energy for the bonds to form here, because they are stronger. That means they're closer together. They gave up some energy in the process. Okay, delta H is exothermic. It's negative. How about the surroundings? Well, we use this formula for the delta S for the surroundings. If delta H is negative, then our term here is going to be positive. We can't tell for sure about the system. We think it's approximately 0. Which means the total would be positive. So this should be spontaneous. All right. So I think I probably added more confusion there. So you do have to be a trained chemist to understand this lingo. Okay, third law of thermodynamics. That talks about a perfect crystal. Only a perfect crystal at 0 K is 0 entropy. Right? And since we can never reach that, we can't reference any of the other entropies against that. We have to reference it against some other place. But entropy does increase with temperature. That's okay. We add energy to the system. So now let's talk about standard enthalpies, right? The thing is, if you don't know what the entropy, if you can never reach zero entropy, because you can never get to zero K, then how do you measure standard entropies? So this is, it has to be calculated. That's the only way. I mean, it can't be measured. Yeah, it cannot be measured. I wonder, let's go back. I wonder if it has something to do with this and this. We can measure enthalpy, we can measure temperature. I bet it is calculated. So if we know the standard entropies of the products, then we subtract the standard entropies of the reactants, just like we did with enthalpies. We do the same thing with entropies. Only the standard enthalpy of an element in its most stable form at 1 atmosphere and 25 degrees C, that's the delta H 0. That's always 0. So that's our reference point for enthalpies. But everything has an entropy, a standard entropy. So this sodium solid has an entropy, water has an entropy, sodium hydroxide. So I guess at this point, we just take it on faith. Okay. And the units of measure are important. This is joules per K mole. So this standard enthalpy is determined for a mole of the substance. So if you have more than 1 mole, like there's 2 sodiums, so you have to multiply that by 2. You have to multiply this one by 2 and that one by 1, then subtract this one by 2 and that one by 2. And you get the enthalpy of that reaction. Okay, you can do the same thing with delta G's. You can either, if you calculate the delta H and the delta S at a certain temperature, then you can calculate delta G, or you can look it up in a table and get delta G's for the products and the delta G's for the reactants and calculate. So let's say a stable diatomic molecule spontaneously forms from its atoms. So let's see. Stable diatomic molecule spontaneously forms from its atoms. So we have 2 X's here, and they have to be gases. Okay. What's the sign of delta H? Well, anytime you take 2 free atoms and bring them together, you give off energy. You give off heat. So this has to be negative. Oops. Well, they're all negative. We're going to explain. Yeah. So delta H, because the molecule is at lower energy than the separate atoms, then delta H is negative. It gives off energy. Delta S is more ordered because we're going from 2 separate atoms to 1 molecule. So that's delta S is negative. So if we plug these into the formula, are they going to show us that? No, they're not. If we plug that into the formula, both of them negative. Let's see, both of them negative. It depends, right? If both of them are negative, if this one's negative, that one's negative, This one either has to be really small entropy, because it's going to be a positive term, or this term has to be very low temperature. So delta G, well, okay. Didn't read the problem, right? A stable diatomic molecule spontaneously forms. If it's spontaneous, that has to be negative. Ooh, that's what happens when you're sleep deprived. Let's see if I can get through this without making any more mistakes. So let's consider this system. PCl3 gas plus Cl2 gas yields PCl5 gas. And the delta G is given as minus 92.5 kilojoules for that reaction. Okay, the question is, these are all gases. So what will happen to the ratio of partial pressures of PCl5 to the partial pressure of PCl3 if the temperature is raised? Okay, let's look at this for a second. Delta G okay, this is negative. We know that. So if the ratio of the partial pressures, what we want to find out is, we know it's spontaneous. What happens if the temperature is raised? Right? If it's spontaneous, then both of these terms together have to be negative. It's at equilibrium. At equilibrium, delta G. Okay. All right. So we're supposed to get a decrease in the partial pressures like that. So what does that mean? Well, if we decrease, if the ratio of partial pressures of PCl5 to 3 decrease, if this ratio to that ratio, PCl5 to PCl3, means that if this decreases, that means we have to get less PCl5 and more PCl3. So the reaction has to go backwards as the temperature is raised. So does that look reasonable? This is probably exothermic. Oh, entropy. We're going from 2 molecules here to 1. So entropy is positive. Okay. And we assume, because we're forming a more stable compound, that it's exothermic. Right? If we do that, then as we increase the temperature, we make this one more negative. We make delta S increase the temperature. We make this term more negative. So increase temperature minus T delta S becomes more negative.
I just read the giant explanation that pops up after.
Oh, okay.
There's still more to it.
Delta S is negative. Delta S is negative. Yeah, it becomes more ordered. That's my mistake. The whole term has to be positive. But delta S is negative. Delta S. Okay. Reaction is spontaneous, that's true. That's delta H must be negative, exothermic, which is favorable.
So as the temperature increased, the reaction proceeds to the left.
Okay. Yeah. If it's exothermic, then we put the energy term on this side, and if we increase the value of that one, it drives it back the other way. Okay. But this is approaching it from the enthalpy end. Delta G is negative. If delta S is negative, which we assume because it's more ordered, delta S is negative, unfavorable. Yet the reaction is spontaneous, that means this one has to be negative. If it's positive, then it doesn't matter what the temperature is. Yeah, okay, I see where they're going with this. Based on the number of moles on this side and the number of moles on that side, this is more ordered than that one is. The product side is more ordered. So the delta S has to be positive. But since delta G is negative, then delta H has to be negative. So we can determine from that the process is exothermic. Then we can use Le Chatelier. Okay. Okay. So free energy can be calculated. Actually, the free energy, as opposed to the standard free energy. Right? Standard free energy occurs at standard temperature and pressure. But maybe we don't want to know the delta G at standard temperature and pressure. Maybe we want to know it at a different temperature or pressure. Right? What we need then is a correction factor. So here it is, the gas constant, and this will be the one with joules in it. 8.31 something or other, 4.5, I think. Joules per mole K, joules per mole K. Then the temperature in K, and the natural log of the pressure. What value the pressure is in? Atmospheres. Let's see a problem to work it out. Or you can use log Q, like whatever the Q is. We'll come back to that. So now we're going to apply delta G to a chemical reaction. Up to this point, we talked about any process whatsoever. Now we want to look at it. Well, we sort of interjected chemistry a couple of slides ago. So a system can achieve the lowest possible energy by going to equilibrium, not by going to completion. Equilibrium may be the lowest possible energy state, right? In this case, it would go to completion, run all the way down off the end. This is what happens for phase changes. But for a chemical reaction, we might end up here where it still produces a little bit of B, but it also produces A, it goes back and forth. And that's the lowest energy. So the equilibrium point occurs at the lowest value of free energy available to the reaction system. So what we're saying is the lowest value for free energy is 0. So the actual delta G for the reaction is 0 at equilibrium. So we can set that equal to, since delta G is equal to delta G0 plus RT log K, and K is the equilibrium constant. We didn't show that one before, did we? We use log P. You can stick a K in here too, a Q or a K, and do that calculation. But if we use K instead, K then says at equilibrium, this is true, that's 0 at K. Otherwise, delta G equals delta G0 plus RT log Q. And then we would have a delta G value if the system is not at equilibrium. But if it's at equilibrium, we can solve the delta G0, and all we need is the temperature and the equilibrium constant, and we can determine delta G0. And once you know delta G0 from that information, then you can plug a Q in here and find out what the actual delta G is. And if you find that the actual delta G for the reaction is positive, then under those circumstances, the reaction is not spontaneous. Just because the delta G is negative, that only says that the reaction is spontaneous for standard conditions. Okay? This is another way to look at equilibrium. We have a gas A going to gas B. We have the free energy for each gas. Here's the free energy for A, and here's the free energy for B under these circumstances. So the total free energy is A plus B, and that occurs right here. So if gas A disappears, G of A decreases. Let's go back. If gas A disappears, the pressure disappears, gets lower and lower and lower here, then that value makes this total less and less and less. And as B increases, pressure of B is increasing. As long as delta GB is less than delta G, or GB is less than GA, the reaction will proceed to the right. So GB is less than GA. That's supposed to be A, and this is B. That does not compute. If you don't mind, I'm going to skip this one. This is more useful, I think. If we have this delta G, standard delta G for a reaction, and we know the K value, then here's the relationship of the two. If K is near 1, right, the natural log of 1, e to what power is 1? Then delta G is 0, it's equal to 0. If delta G is less than 0 or negative, then K has to be greater than 1. And if delta G 0 is greater than 0, then K is less than 1. Okay. So for non-spontaneous reactions under standard conditions, the K would be less than 1. So you have a very, very small K, and that means that you mostly reactants. And delta G is, okay, so that verifies the fact that if this is positive, it's not spontaneous. And the K says that you're mostly reactants, which is in agreement. But if K is large, then it's mostly products at equilibrium. And delta G0 is less than 0, which means it's spontaneous. I'm not so sure about this one, just because K equals 1, right? Because we know that you can have all kinds of Ks, size Ks, depending on the reaction. So I think this probably should say approximately 1. Delta G equals Now this one is true, delta G0 is 0. That's an equilibrium. Okay, so let's get back to Gibbs. Gibbs wanted to know how much free energy was available from a reaction to do work. So that means the Gibbs free energy is equal to the maximum available work that can be extracted from a process. But maximum work can never be reached. That's a theoretical value. Right? And it only occurs for reversible reactions on the very smallest scale. They could easily go back and forth. But all processes are irreversible. If they're going to go spontaneously, they will not go back the other way. So there must be something else involved here. If this is the maximum available amount of energy, then there must be some loss somewhere. See, that was kind of out of position, wasn't it? Hang on to that thought. So what we're looking at is an equilibrium point, which occurs at the lowest value of free energy available to the system. The lowest value of free energy. And we're talking about the delta G actual, not the delta G 0. So the delta G actual would be equal to 0. That's the lowest amount of free energy available. That's equilibrium. So we set this equal to 0, and now we have delta G equals to minus RT log K. Okay. Now we're going to do some equivalence here. Delta G0 is also equal to delta H0 minus T delta S0. So this Gibbs equation now is equal to this version at equilibrium. So if we divide through by RT, right, we divide it through by RT, it leaves this log K on one side and puts minus RT on both sides. So this minus changes that one to positive. Now we have, let's see, I'm with it down to this point. Log K equals delta H0 over minus RT, and then minus T delta S0 over minus RT. Okay? So now, what does that give us? Well, this one now is positive. This one is negative. This T cancels. Oh, okay. So let's pull this term out. Minus delta H0 over R times 1 over T plus delta S0 over R is equal to log K. Okay. I see where they're going with this. What does this look like? Y equals NX plus B. So if you plot log K on the y-axis against 1 over T on the x-axis, then the slope of the line is going to be negative delta H0 over R. And the intercept is going to be delta S0 over R. Okay, here we go. So here's our X, 1 over T. Here's our Y, natural log of K. So you have different K values for different temperatures. And if you plot those and find the solution for it, then this value right here, minus 11,645, is equal to minus delta H0 over R. So you divide R into it, the negative goes away, and you find out what your delta H is for that reaction. And if you find the intercept, then you take that value and you multiply it by R. I should have said multiply. You multiply this value by R, and that cancels R. Multiply this one by R, and that cancels. And you can determine two things: the delta H0 for that reaction and the delta S0 for that reaction. That's the whole point of that exercise. So what is it going to look like on a test? I might give you a graph with this on the x-axis, this on the y-axis, and say this is the y-intercept. What's delta S? Or read it off the graph. Or I might say, here's the equation of the line. Find delta H. You look at the slope and do the calculation for the slope. Okay, back to maximum available work. This is the maximum available work is only available under a hypothetical situation in which the process is infinitesimally reversible, where you can make just very minor changes. All real pathways waste energy in the process. So the maximum work won't be available. Okay, these are statements about the laws of thermodynamics. I thought they were cute. First law, you can't win. Because the delta E is for the universe is 0. So you can't come out on top. It always sums to 0. You can only break even, which means you can only change energy from one form to another. But the second law says you can't break even because any transfer of energy is going to waste it. Right? And unless the waste energy is delivered to an absolute 0, then you're not going to get any work out of it. So the second law says you can't even break even. The third law says you can't get out of the game either, because you can never get to absolute 0 to do this. So it's hopeless. Thermodynamics, it makes a what do they call it? An ethical statement about the universe. It's all hopeless.
Depressing, but okay.
Yeah. Chemistry, psychology. So the takeaway from this is every time we use energy, we degrade its usefulness. Now on the minor scale, you can take one process and couple it to another one, and one spontaneous process can be used to drive a non-spontaneous process. Allergies.
Yeah.
Yeah. Is there something in this room or just something in the air?
I don't know. I think it's just something to go with the season right now.
Oh, okay. You're allergic to chemistry.
Maybe.
Okay, that's it.